We'll have Ryan Clay get us started.
Thank you. My name is Ryan Clegg. I'm a grad student at Washington University in St. Louis. I work with Brad Jolliffe, and I'm going to tell you what I do in poetry form. All right. Lunar landers descend to the surface, the engines providing great thrust. Exhaust scours the lunar surface, disturbing large quantities of dust. Dust sheets obscure visibility, particles fly low and fast. Fines travel kilometers away as the plume expands into a cool gas. For future lunar operations, we must understand this blowing soil. For hardware and outposts it can damage, and entire missions it could foil. Blasted by spray from Apollo 12, Surveyor 3 fell victim to this threat. Returned pieces were pitted and cracked by soil blowing in the gas jet. The rocket exhaust has disturbed the soil, and at the Apollo sites we see an elliptical area of disturbance with an increase in reflectivity. We call these disturbed areas blast zones. Luna and Surveyor sites have smaller ones. High-resolution images from LROC have allowed spatial measurements to be done. What physical properties cause this change? We are currently testing several hypotheses, but if it's answers that you want, my talk on Wednesday, you'll have to come see.
That was great. And one small change in the schedule, we have Anthony Hsu who will be talking instead of Stephen Lord.
Hello, my name is Anthony Hsu. I'm a physics grad student at the University of Colorado at Boulder. For the last 3 years, I've been helping to build and run a 3 megavolt dust accelerator at the Colorado Center for Lunar Dust and Atmospheric Studies. This accelerator has been used in different experiments, from looking at light flashes from micrometeorite impacts to helping calibrate the lunar dust experiment aboard LADEE. My research is focused on looking at the microcraters that are formed by these dust impacts in various materials. Currently, I'm focusing on a material called polyvinylidene fluoride, or PVDF. So if you'd like to learn more about PVDF, its use as a dust detector, then stop by poster 19, Cratering Studies in Thin Plastic Films. I will be there between 5:30 and 7:30 tonight. So thank you very much.
Hello everyone, my name is Michael Poston. I'm a graduate student in chemistry at Georgia Tech, and I'm interested in volatiles on airless bodies, especially water on the moon, the sources, the evolution, and the eventual fate of these volatiles. My research currently involves both experiments and modeling. I do experiments in the ultra-high vacuum chamber that I helped design and build to measure the desorption energy it takes to get water to come off of the lunar regolith. The measurements we use here, the numbers we get from these measurements should be helpful in making lunar models of water transport more accurate, and also supports the idea that there could be a submonolayer veneer of water at high latitudes on the moon due to chemisorption, which I can tell you more about if you come talk to me. But here at this conference, I'll be talking about the modeling work that Greg Greaves and I are doing regarding hydroxyl being formed by the solar wind and then diffusing within a single lunar grain, and where it ends up, how much there is left, and how much can be produced, how much water or hydrogen could be produced by this process. So again, my name is Michael Poston. I'm giving a talk actually on Thursday morning here on this stage, and I'm a graduate student at Georgia Tech who will soon be looking for a job. Thank you.
Good afternoon, everyone. My name is Patrick Donahue, and I'm working at the University of Notre Dame with Clive Neal, starting my 5th year in PhD studies. And what I do there is we're trying to work out the petrology and petrogenesis of some of the Mare basalts from the samples that we have returned, and specifically the Apollo 17 high titanium basalts. I'll have a talk this afternoon, or not this afternoon, Friday, the second to last talk. Thursday is the last day of the conference. Okay, second to last talk, Thursday, 3:35, talking about this really interesting olivine cumulate sample it was a rake sample from the moon, and working to bring that back into the other samples that we have as well. So hope to see you then.
Good afternoon, everyone. My name is Jesse Davenport, and I'm a second-year graduate student at the University of Notre Dame working with Clive Neal. And my research is I work on the crystallization and evolution of the lunar magma ocean. I'm working on an all-encompassing model that brings together things such as geochronology, remote sensing, sample petrology, and geochemistry, and numerical modeling. My poster this week is at booth 39. And it is a portion of this research where I take rock lithologies thought to be crystallized from the last dregs of the lunar magma ocean, and I model them backwards to find a bulk composition associated with these rocks and compare it to past and recent bulk moon compositions. Again, my name is Jesse Davenport. I'll be at poster 39. Thank you.
Hi, I'm Rebecca Samod. I worked at Space Sciences Lab as part of UC Berkeley with Andrew Poppy and part of Greg Delory's group. We're studying Artemis observations of pickup ions in the terrestrial magnetosphere tail lobes. So pickup ions are primarily produced by photoionization of the neutral exosphere and picked up and accelerated away from the moon by electric fields. So using everything that we know about pickup ions and the really quiet, calm environment of the lobes, we're using Artemis data to trace ions backwards from where we observe them to potential source regions on the moon, and also doing some forward modeling of the ion trajectories. So our ultimate goals are, well, not ultimate, but our current goals are to constrain the ion source regions and masses in order to build a more complete picture of the exosphere, its constituents, its source processes, and its loss processes. I'm at poster 34. My name again is Rebecca Samad, so please come by and talk to me. I'd love to talk to you.
Great, thank you so much. That was wonderful. I love the